So yeah, I don't know if people have read the abstract, but it's a little bit different from the abstract, but it still covers what's in the abstract, but the talk's now got a bit of a different focus. So what it's about is the question of what is a formal proof in general. So like we're all familiar with many definitions of formal proofs, in particular systems, but then the question I want to ask is what is a formal proof in general? So what makes all these things systems of formal proof and some other thing not a system of formal proof? So I think the first thing we can say is that a formal proof it's not just a proof, it's a proof of something, and it's a proof in a certain proof system. And then the question becomes, well, what's a formal proof system? And so I think there's two essential features of a proof system. And this is sort of stuff that I've never seen anybody exactly say it, but on the other hand, once you have this in mind and you look at things people do say about particular proof systems, it kind of seems like in the air rather than something that I've just completely made up. But at the same time, nobody's ever actually said it as far as I'm aware. So what is a proof system? Well, there's two kind of essential features of it. One is that it involves a specification of the symbols that are allowed to appear in proofs, and of the format of a proof, how these symbols can be arranged to form a proof. And so given those two things, I think we can say that any array of those allowable symbols in that allowable format is what I would then call a proof candidate. And then the second part of specifying a formal proof system is to give some decision procedure that will take some claim of the kind of which you can prove things in that system and some proof candidate. And then this procedure will, given those two inputs, so these are the inputs I was talking about well, no, sorry, not quite. Okay, so given these two inputs, the decision procedure will then say, yes, this is a proof of that claim. This proof candidate is in fact a proof of that claim, or no, it isn't. Okay, so that stuff I think is I think we can just sort of take that as being pretty much in sync with stuff people actually say about particular proof systems, even though, as I say, I don't think anybody has quite said this. But then there's another idea that you can find in the literature, and that's what I want to talk about in this talk, whether we should add this further requirement on what it is to be a formal proof system. And okay, this is the thing I just said. So, oh no, I didn't quite say this. Okay, so that's what a proof system is. Yeah, it defines the symbols, the format, they give you proof candidates, and then there's a decision procedure that says of a candidate whether or not it is a proof of some claim. And so what's a formal proof? Well, a formal proof, of a certain claim in a certain system is a proof candidate of that system that the decision procedure for that system says is in fact a proof of that claim. Okay, so that I think we can sort of take that as a kind of starting idea of what a formal proof is. And then there's this question of should we add this other thing? And that's what I want to talk about. And so in this talk, basically I want to say we shouldn't add this further requirement. And so the additional requirement that you see in some places in the literature is that this proof checking decision procedure must not simply be an effective procedure or a mechanical procedure, which is what I was assuming when I called it a decision procedure. It must also be feasible, which is normally taken to mean polynomial time. Okay, so this idea you can find in, for example, this article by Urquhart. It originally seems to come from some papers by Cook and Rakow in the 70s. Can't really see it very clearly, but there's some bits that are highlighted in here, but they're too pale. So it says here, we need a general definition of the proof system up here. And then start here with this bit. The crucial property of a proof system as defined above is that given an alleged proof, that's what I'm calling a proof candidate, there is a feasible method for checking whether or not it really is a proof. So of what it is a proof. Okay, so the method has to be not just effective, but feasible. The idea is also in this other article, again, referring to Cook and Rakow. So just a bit for the moment to look at is this bit at the bottom. You can't really see the highlighting that says we identify a proof system with a polynomial time procedure that checks the correctness of proofs. So again, you have this proof checking procedure, but it's furthermore has to be polynomial. Okay, so why? So I'm going to say we shouldn't. This shouldn't be part of our very idea of a formal proof. So the question is, why would we think it should be? So I think there's this sort of bit up here is supposed to be highlighted in green, and I think there's kind of two things you can extract from it. I'll look at those two, and then I'll make up a third argument for why you might want this added sort of feature or added requirement. And I'll argue against that as well. That's going to be the shape of the talk. So the first thing I think that you can get out of this bit that's supposed to be highlighted is this. It says here, the key observation is that a proof is easy to check. Okay, so that's just kind of presented as like, there's no argument for that. It's just seems to be said as something that's meant to be kind of intuitively obvious, or not obvious, but intuitively appealing. If I go back to the Urquhart quote, again, it's just presented. The crucial property of a proof system is that there's a feasible method. Okay, so on the one hand, you have the idea, well, look, it's just intuitively appealing. But I think against that, I want to sort of present some exhibits from the literature. So if you go to Hughes and Cresswell's famous introduction to modal logic, they have these proof systems. So there's some supposed to be highlighted bits here. In the proof system for K, start here, it says its axioms consist of all valid well-formed formulas of PC, that is of the propositional calculus. That is all formulas specified by the following axiom schema. If alpha is a valid formula of PC, then alpha is an axiom. Okay, so then here's, for example, is an example of a proof. I don't know if you can see the top line because it's covered by that box, but what it says is we shall prove two theorems in full detail. So that's kind of important. So they don't view this as some sort of abbreviation that could be spelled out into a formal proof. It says we can prove things in full detail. And then if you look at this proof, it has these lines like the first line is just an axiom. And this line here, PC2, is just an axiom. And so you think this doesn't meet this requirement that the proof checking method be feasible, because we don't have any feasible method for just checking in general whether a formula is a valid formula of propositional logic. But we can't have one if P, unless P is it. Okay, so that would not be a proof if you added this further requirement of feasibility, but Hughes and Cresswell think it's a proof, not just an abbreviation of a proof. And so, as far as I'm aware, does everybody who's read that book. I'm not aware of anyone saying, hang on, there's something wrong here. And John Burgess, in his book Philosophical Logic, does the same thing. He says, in the context of tense logic this time, says you can have as an axiom A, where A is any tautology. So you get the same issue. And he also has another thing where he says, actually has this rule of tautological consequence. So, it's a rule of inference where from some stuff, you're allowed to infer some other stuff that follows validly from it. So you can look at an example of a proof, and you can say that like the third line follows from the first two by this rule. But again, we don't have any. So to check that proof, you'd have to say, well, does the third line really follow validly from the first two? We don't have any feasible procedure for checking that. Okay, so the upshot, now actually just to, full disclosure, Burgess does say of this rule, it's a derived rule. It's not a primitive rule of the system, but I don't think it would make any difference if just like I think it's fine to take the axioms as valid formulas, it would also be fine to just have as a primitive rule this rule. Okay, so that's the first response. You can kind of take that in two ways. It's like partly you could say this is an argument from authority that people like Hughes and Cresswell and Burgess think defines proofs, or you can just take it as a kind of appeal to your intuition to look at these things and agree that they're fine. They are formal proofs. Okay, so if we go back to this quote, there's another thing in this green, what's meant to be highlighted in green, this bit up here, which is a kind of argument, not just an appeal to intuition, but a kind of argument. And what it says here is, since there are only finitely many truth assignments to check, why not allow the statement itself as a proof? So if you just went with my original definition of a formal proof, the thought is, well, look, you could just say, just write down the formula propositional logic, and we say that's its own proof. And then we say to check whether this, to check whether this formula really is a correct proof of itself, you do the thing that we would normally regard as constructing the proof, say truth table or whatever, but now you just view that as the procedure for checking whether or not this thing really is a proof. And seeing as that's an effective procedure, that would be completely fine according to the original definition of a formal proof. But they say, then they go on to say, what extra value is there in a filled out truth table or a derivation using some axiom inference scheme? And then the bit that I said before, the key observation is that a proof is easy to check, unlike the statement itself. Okay, so I think you can sort of say, well, there's a kind of argument here, which is that intuitively we don't want a formula to count as its own proof. So we need to add something to the original specification of what a formal proof is, or else every formula of propositional logic will count as its own proof. And my response to that argument is that it doesn't work. Like, ultimately, I don't think there is anything wrong with regarding a formula as its own truth. But if you do think there's something wrong with that, then this won't solve the problem. So that's the sort of the next bit of the talk. So I just want to introduce a certain kind of formula. And so just for convenience, sort of think of the basic propositions or propositional variables or sentence letters or whatever you want to call them. They go by different names of this language of propositional logic written as P1, P2, P3. And then a conjunction of distinguished literals will be a conjunction of literals where none of those basic propositions appears more than once. So there's some examples here. But basically, you can't have something like P1 and not P1, or P1 and P1 where it appears twice. And so given one of those things, it's conjunction of distinguished literals, you can talk about its signature, which is just the sequence of subscripts of the basic propositions that occur in it. So here are the signatures of these formulas. So it's just the numbers on the basic propositions in the order in which they appear. And then you can say that two of these things are cosigned. They have the same signature. Okay, so then the kind of formula that I want to talk about is what I call a cosigned disjunctive normal form. So it's disjunctive normal form where the disjuncts are these things that were on the previous slide, these conjunctions of distinguished literals, and they all have the same signature. So there's an example of one. So like 275, 275, and 275. And they're all distinct. There's so that, yeah, it's a conjunction of, a disjunction of distinct ones of these things. They don't repeat. Okay, so a quick way of sort of getting into your head what these formulas look like, and also of seeing something else familiar but useful to remember at this point, is that if you just take this thing here is just any old formula at all of propositional logic. And if you do its truth table, then you can sort of read off this truth table a formula over here that's equivalent to it. And this formula up here is going to be in that form that I just introduced. So you say, well, look, to make this thing true, you either have to do what's on this row, P3 and P1 and P4. That's the first one. Or you have to do what's on this row, which is P3 false, i.e., not P3 and P1 and P4. That's that one. Or you have to do this, or you have to do this, and so on. So if you read off a formula in that way, you'll get one of these formulas of the form I'm interested in. And also what this what this illustrates is every ordinary formula, for example, that one is equivalent to one in this form that I'm interested in. Okay, so the thing about these things is that those kinds of formulas you can regard them as their own proofs, and the proof checking procedure is feasible. So yes, you can't see that. Oh, I guess so. Okay, so you can regard a formula of this kind as sort of simultaneously like a proof candidate of 3 different claims. And so the claim that it itself is unsatisfiable, the claim that it itself is satisfiable, and the claim that it itself is a tautology or valid formula. And then well, which of those claims is it actually a proof of? Well, the one or ones for which it passes the proof checking test. And that test is here at the bottom of the slide. And this is feasible. So the first thing you say is, well, look, is the formula bottom like that? That's the disjunction of 0, these things. And if it is, then we say, okay, so it's unsatisfiable. And if it isn't, then it's satisfiable. So basically, they're all satisfiable except the one that has no disjuncts at all. And the reason for that is if you go back to this slide, if there's even one disjunct there, then it basically just tells you right there how to make the formula true. Like you just make P3 true, P1 true, and P4 true, because then you never have the same, you're never going to have like P1 and not P1 because they're just distinguished. So if there's even one disjunct there, then the thing can be true. And in fact, it's just telling you right there how to make it true. And so then, okay, so if we find out that the thing's satisfiable, we can then go on to ask, well, is it a tautology? Is it true no matter what? And so the procedure for working that out is, well, just count up, go to the first disjunct and count up the number of basic propositions in it. And then go across the whole formula and count up the number of disjuncts and call that second number m, and then just say, well, take this number m and can you keep halving it and then halving the result and so on? Can you do that n times? And if you can't, if you run out of, number to halve, or you get to an odd number that you can't halve exactly, then the formula is not a tautology. And if you can halve it n times, then it is a tautology. So what's going on there? Well, the thought is, like, if you can halve it n times, then what that means is like the total, well, this is a case where you can't, but what it would mean is the total number of disjuncts there was, which I'm calling m, is 2 to the power n, where n is the number of formulas in each one. And as we already said, like each disjunct kind of tells you how to make the formula true, like what truth values to assign to these basic propositions to make the whole formula true. And if there's n of them, then there are only 2 to the n ways of assigning truth values to them. So if there's if there's 2 to the n different disjuncts in this formula, then you've covered them all. It's like however you assign the truth values to the basic propositions, these things are going to come out true. So it's a tautology. Okay, so how am I going for time? How am I going for time? When did I start?
You should be okay. You can continue because 6 minutes more. Okay. So you should end at 10:06 because we were late.
Oh, okay. So I can just briefly talk about the next 2 slides. So that was just about taking a single formula to be a proof of its own satisfiability or unsatisfiability or validity or whatever, as the case may be. You can do the same thing for sets of these formulas, as long as all the formulas in the set have the same signature. Then you can take that set of formulas to be a proof of its own satisfiability or unsatisfiability, as the case may be. And the test is just this thing in blue. You just say, is there some disjunct that appears in all the formulas? Or in other words, is there some way of making them all true? So then the set's satisfiable. If not, it isn't. Okay, and similarly, if you take an argument, as long as the premises and the conclusion all have the same signature, then you can take that argument as a proof of its own validity or a proof of its own invalidity, as the case may be. And to check whether it is, you just say, you know, is there some disjunct that appears in all the premises and is not in the conclusion, or in the more familiar way of putting it, you know, is there some way of making the premises true without making the conclusion true? Okay, so the point is, and then of course you can say, well, we can just consider a language in which only these kinds of formulas are well formed at all. There are no other formulas. And everything that you can express in the ordinary language, you could express in this language. There's an equivalent translation. So in this language, every formula would be its own proof. So if your motivation was kind of, well, we just don't like the idea of a formula being its own proof, then adding this feasibility condition doesn't help. So that's not a motivation for doing this. Okay, so the final reason I want to consider of why you might want to say that proof checking has to be feasible, it's part of the very idea of a formal proof that checking a proof should be feasible. This isn't something I found in the literature, but just thinking about it, I can imagine someone might say something like, well, look, proof fundamentally is an epistemological notion. Like what a proof is supposed to do is establish the conclusion as being true. In other words, it's got to get you to know the conclusion or be certain of the conclusion or something, some epistemological notion. And then they might say, well, look, you don't actually know the conclusion until you check the proof. So if I just give you a proof of some theorem, you don't know it. You have to actually check it. And so therefore, in order for proof to kind of do its job, which is get you to know something, you have to be able to check it. So the checking procedure has to be feasible. Now, I think that this is not a good argument. And there's there's sort of two things I can say against it. The first thing is that it proves too much. Because suppose that, you know, I just said if someone gives you a proof, then in order to know the theorem, you have to check it. But in order for the proof has to come from somewhere. So if this is true that you can't kind of know the theorem until you've checked the proof, well, you can't check the proof until, you know, you don't necessarily have to construct it yourself, but somebody has to construct the proof. So by this kind of reasoning, it would seem to follow that there has to be a feasible method for constructing the proof in the first place. But as I already mentioned, we don't have any such methods, and there aren't any unless P equals M. So it proves too much. And so what's wrong with it? Well, I think what's wrong with it is it's kind of mixing up this notion of feasible in the complexity theory sense with kind of can in a more, can in the sense of what we mean when we say you can know this theorem is not, I don't think, the same as what the complexity theorist is talking about when they say the procedure has to be feasible. So you can sort of see in a way that by seeing that feasibility is neither necessary nor sufficient for kind of can know. So this notion of feasible is about the rate of growth of a function, whereas I think this ordinary epistemological notion of can you know it is just simply about the sheer size of some number. You know, do you have time to go through this? Right. So if you think about proofs in propositional logic, we do have you know, for things like truth tables or whatever, we have feasible methods of checking them. That doesn't mean that you can know every theorem that has a truth table proof, because some of them are just too big. It's not about the feasibility of the procedure. It's simply about how much time do you have to check the thing before, you know, you die or the universe, whatever. But the fact that you have this kind of feasible procedure doesn't mean that you can actually know the theorem at the end of it, because you just don't have time to check it. So it's not sufficient. And I think it's also not necessary, because suppose, you know, you have a proof of some theorem and you can check it in the ordinary epistemological sense. You have time to go through it. Well, then you actually have time to construct that proof. There's the same number of steps to construct the truth table as to check it. So it seems like you can construct the proof. Like you can, because you have procedure a mechanical procedure you can follow to build the truth table. And there's not too many steps involved, so you can construct it. So in that case, you can do something even though that you don't have a feasible procedure for doing it. In the other case, you do have a feasible procedure for doing it, and yet you still can't do it. That is, check the proof that's too long. So I just think this argument is kind of mixing up these two notions. So it's not a good argument. So ultimately, I think the original, what I had up there originally as the notion of a form of proof should stand. We shouldn't add to the very idea of what a form of proof is, that the proof checking part has to be feasible. So that's it.
Just for clarification, I got lost a little bit at the end. So you're not saying that you can construct a proof in a feasible